Real life.
Yeah. Hello everyone, welcome to the final day of MLRW 2022. I am Ayush and today we have Mr. Dr. Pranav Rajpukar with us. Mr. Rajpukar is an assistant professor at Harvard Medical School. You might also be familiar with his AI for Medicine Coursera course. He is also the author of widely used SCOT dataset. SCOT dataset is the widely most popular dataset for question answering. Without any further delay, I will hand over the stage to Pranav to start the talk.
Great. Thanks for having me here. Today, I'm going to share a little bit about my research and about the field of medical AI. My lab at Harvard Medical School works to build and translate medical AI to the clinic. And broadly, we work on three directions. One of them is label efficient medical AI, where we're moving from algorithms that require a lot of label data to algorithms that are label efficient. The second part of the lab's work, and which will be the second part of my talk today, will be on Clinician AI collaboration, where we're moving from this idea of let's compare how well models perform to doctors to this idea of how do models perform with doctors. And then finally, I'll talk about open benchmark curation, where we're seeing this need to go from these private data sets to diverse public data sets. I'm going to focus on imaging and sensor modalities today. In my lab, there are about 30 members training in artificial intelligence or medicine, and we work across a variety of hospitals and industry partners. Great. So without further ado, let's get started. We'll chat first about label efficient medical AI. There have been rapid advances in medical AI over the past 5 years. There are now over 100 FDA-cleared technologies, many in radiology and cardiology. There are over 6 randomized control trials in gastroenterology, ophthalmology, and there are 2 AI algorithms which have received reimbursement codes in the US. This includes for detecting diabetic retinopathy in ophthalmology and also looking at CTs to detect strokes. But the difficulty with these algorithms is if we think about what it's going to take to scale from doing these 100 or so tasks to doing every task that is within the domain of a clinician like a radiologist or a cardiologist, it's quickly going to be difficult and expensive to scale this labeling for every task. And so what can we do about this? Broadly, there are 2 class of solutions I'm going to talk about: transfer learning and self-supervised learning. Let's start with transfer learning. The idea behind transfer learning is I'm going to start learning on a set of natural images where the task might be, in this photo, what is the object in this photo? Is this a penguin? Is this a cat? Or is this a dog? And then I'm going to learn that using millions of such natural images. And that serves as a starting point for fine-tuning on a medical imaging task where, given a medical image like a chest x-ray here, the task is to say, is this a mass? Does this have a mass or no mass? Is there a pneumonia here? Is there edema here? And so on and so forth for several diseases. And this is the idea for transfer learning. And this idea works really well for medical images. Here's an example of an MRI. And so an MRI looks at the knee, and we're tasked with saying what abnormalities are there in this MRI. And so we can break down the MRI into different slices. And on each slices, we can apply this pre-trained network and then put all of the predictions together to say, in this MRI sequence, was there an abnormality? And using 1,000 training examples, we can do well for the abnormality detection and several specific diseases. So a couple of years ago, we were thinking about what we could do for 3D medical images using what we learned from 2D medical images. And so the basic idea is if a image of a penguin is helping to learn for a slice of a medical image, like a slice of an MRI, then can I use videos, and specifically videos of people doing activities, to be able to improve learning on 3D medical images? And so that's what we did. And here's an example. So in the first step, what we do is we take a bunch of videos on YouTube and we train a network to recognize actions in that video. And then we use that as a starting point to learn a network that first looks at a CT scan, and from that CT scan is able to determine if there is appendicitis in the abdomen. And so we apply this to several different models. And on the right, you can see with pre-training, we're able to perform much better than without pre-training. Great. So this idea of video pre-training as a form of transfer learning works really well, not just for MRI, but also for other modalities. Here are two examples where it works for modalities like a CTA on the left, where we're trying to detect aneurysms, and on the right, on CT scans, where we're trying to detect pulmonary embolisms. So that was transfer learning. Another class of methods which has been gaining popularity recently is self-supervised learning. And the idea behind self-supervised learning is I'm going to use a lot of unlabeled data to learn some task of interest that is called the pretext task, and then use that as a starting point for fine-tuning on labeled data where I now do the task of interest. So for chest x-rays, what this might look like is the pretext task could be look at an image, look at a transformation of that image, and have them be mapped to the same space, while look at one image, look at another image, have them be mapped to different parts of higher dimensional spaces. So using this methodology, on the bottom right, you can see that a self-supervised strategy, here MoCo pre-training, can do better than the traditional strategy of pre-training on a data set like ImageNet, where you see that for small fractions of labeled data, you're able to get an improvement in performance using the self-supervised learning strategy. This is a very powerful paradigm, and one of the future avenues of exploration here that's very powerful is looking at heterogeneous data sources. So if we have mobile data, if we have genomic data, if we have medical imaging data and EHR, and we're able to combine some of these different domains together in order to enable learning these different aspects of the physiology, then we might expect to do better in terms of learning good representations that allow us to learn different tasks of interest with a small amount of labeled data. So that was the first part of my talk, where we talked about label efficient medical AI. I now want to talk about clinician AI collaboration and what this world in which we're evolving from a clinician versus AI setup to clinician with AI setup could look like. And I want to start by sharing an example of a study we did with physicians in South Africa, where the task was to determine whether a patient had active tuberculosis based on a combination of their lab values and a chest x-ray. And we were looking at HIV positive patients. So on the right is an example of what this interface would look like, where for a patient, a physician would see their lab values and then their x-ray, and they have to make a determination of whether this is active TB. So we have a version of the interface here where we're able to show the outputs of an algorithm in the form of a heat map and in the form of an algorithm TB prediction, and also for some cases, not show the AI in order to measure what is the improvement that one has with these AI algorithms that are assisting the physicians. And so on the left, you can see what this assistance looks like, where the heat map highlights the parts of the image that are most consistent with tuberculosis. And the algorithm also outputs a TB prediction from very unlikely to very likely. On the right, you can see that there are cases, which we call training cases, where before the study starts, the physicians get to test their knowledge and also calibrate themselves to the AI model by, for each case, they answer whether or not they think it's active TB and get the ground truth established by the microbiological standard, which says you were right on this case. The true diagnosis was negative, but you chose unlikely, or you were wrong, you chose likely. And so after they do this training, they do the experiment, and then we're able to compare how they perform with and without assistance. And we see that with assistance, there is an improvement in accuracy from 0.6 to 0.65. Some of it is because of an increase in sensitivity. Some of it is because of an increase in specificity. But what was surprising about this study was that if you had the algorithm run by itself in the standalone format, the algorithm had a much higher accuracy than the assisted clinician. And this came not from an increase in sensitivity. You can see the sensitivity actually goes down by a bit, but a big increase in specificity. And what this translates to is that if someone does not have TB, the algorithm is able to more correctly call that that person does not have TB. We can look at the performance of each individual physician as part of this experiment. And what you can see here is in gray, their performance without assistance, in blue, their performance with assistance, and then the cross represents the model's performance on those particular cases. And what you can see here is that some physicians have a big improvement in performance. You can see this physician had an improvement from the mid 0.5s to the mid 0.7s, while other physicians, like this one over here, actually had a reduction in their performance with assistance. And this could be due to a variety of factors. This could be mistrust in the algorithm's output. This could be overconfidence in one's own diagnosis. This is a very active area of work, and my hope for the field is that we understand this idea that just because we have expert level AI, we're going to improve clinician performance is misguided. And for us to be able to effectively enable this collaboration, we need to be thinking about experience levels, about clinician interaction, about case difficulty, and about automation bias. So the final part of the talk, I want to talk about open benchmark curation. The idea behind open benchmark curation is that medical dataset curation is hard because it requires partnership with hospitals. It requires IT frameworks for de-identifying and pulling. And maybe most expensive is the manual annotation itself. So what can we do to enable progress here? Well, one very neat idea came from the NIH release of a large chest X-ray data set with 100,000 examples, where they said the following: in order to label chest X-ray images, I'm going to look at the corresponding radiology report, which was dictated at the time of image interpretation. On this radiology report, we can now apply a report labeling natural language processing system, the goal of which is to determine whether a disease is present, absent, or uncertain, and thus label the image accordingly, 1 if it's present, 0 if it's absent or uncertain. So this is a neat idea, but the unfortunate part about this is that it's very easy to have a high label noise as a result of using this process. And that's what happened with the NIH Chest X-ray 14 data set. This is an example from a blog post where a radiologist took a random sample of images and highlighted ones that were incorrectly labeled, where the radiologist disagreed to the report labeling NLP system outputs. And so we started tackling this problem, and I want to share a little bit about what this problem looks like. So on the left, we have a radiology report, and we're going to go from that report to the labeler output on the right, which annotates for the presence or the absence of every single disease that we're hoping to classify. And so here, as an example, we look at cardiomyostinal silhouette, and that's a mention which we want to extract of a disease. And then we want to associate it with an attribute, which is here unremarkable. So what we do is for this mentioned cardiomediastinal silhouette, which corresponds to the enlarged cardiomediastinum observation, we look at unremarkable and we say, okay, this means we're negating the existence of that and therefore having a labeler output of 0. We might have other attributes to assign, such as the uncertain attribute. So here it says atypical infection or chronic fibrotic change, and the or signifies that the infection may be there, it may not be there, we're uncertain about it. And so that corresponds to pneumonia being uncertain. Of course, some are simpler, where we simply have a mention specifying the existence of something, like for fractures. And so for fracture, we input A1 here. And so this is an automated process which is handled by a natural language processing system. And so we built this system out and we apply it to a large corpus at Stanford and show that it improved over the previous state-of-the-art labeler. We also applied it to a data set that was being constructed at BI with faculty at MIT and collaborators at Harvard. And this was the Mimic CXR data set, which you may also know about. And Chexpert is the data set that we released from Stanford, which is one of the largest data sets and competitions for automated chest X-ray interpretation. And it's been part of a larger effort to make data public and establish competitions to track the progress of AI algorithms on these very different tasks. But in some ways, one of the challenges for the future is that these data sets are really toy task setups. If we think about what it's going to take to go from the kinds of tasks that algorithms are solving today to the kinds that they need to solve in order to integrate well into clinical practice, we need to be able to think about how we bridge this gap. And some of the ways in which we need to bridge this gap include increasing our coverage of diseases, increasing the heterogeneity in the patients, increasing generalization across clinical workflows, thinking about how we can use clinical context and priors in order to make predictions. I want to share one example of how we're tackling this. So for poor coverage of diseases, one of the ideas that we've been exploring is how we can go from a radiology report to a graph that captures all of the important information about the existence of diseases and their relationships to anatomies or to uncertainties as are mentioned in the report. And so we did this with a recent effort called RADgraph, where we go from the report on the left to the graph on the right, which summarizes the observations for that particular patient. And we've made this a publicly available resource. I want to end by talking a little bit about our efforts to establish a larger community around AI medicine. So one of the aspects that we've been working on is building education materials. And as part of this, I helped develop a massive open online course called the AI for Medicine Course Specialization, which can be found on Coursera. I co-host the AI Health podcast, where we talk with entrepreneurs, investors, and scientists in the space of health AI. And I co-edit a newsletter called Dr. Penguin, which summarizes weekly the advances going on at the intersection of AI and medicine. At Harvard and at Stanford, I lead a joint program for closely mentored research at the intersection of AI and medicine. I want to end by thanking several students and faculty that I was grateful to be a part of collaborations with, and a lot of the work you've seen today was done in collaboration with folks on the slide. And I will end there. Thank you for having me.
Thanks a lot, Pranav. That was very interesting talk. And we have some questions. One question is from Jayashree. Can you explain pre-training on images? What tasks do you train the model on?
Sure. So pre-training on images, the typical setup is to use ImageNet. So with ImageNet, there are, in the traditional ImageNet, 1,000 classes, and these might include things like a chair, a table, to a animals, different cats, different dogs. And so those are natural images paired with labels from 1,000 classes. And that's the starting point for the pre-training task.
Yeah, thanks a lot. I have one question. Like, as we know that like the data is most challenging aspect of any problem, and like in medical AI, like getting some data because like when we are concerned with medical medicine and health is involved, like there's concern of privacy, like the data cannot be shared. Like how we how we solve this barricade because like in NLP nowadays like weak supervision is very famous like to like when we have a small data set like we use various kind of weak supervisors to label them and then train a HMM or a generative model. Like is it possible to do something similar in computer vision?
Well, I think of it in two ways. One of them is, what can we do technically to be able to work with data that has um, private information associated with it. And this shows up, as you mentioned, all the time in medicine. And on the technical side, some of the things people think about is, how do you train private models? How do you train models such that you can tell whether a certain patient was used to be able to train the model, or to be able to reconstruct any patient's identity given the information in the model? So that's one. The second set of approaches might be something like federated learning approaches, in which um, there are local updates made to a model, and those are sent over centrally by some sort of aggregation that makes it difficult to identify individual patients that were used to train these models. So that's on the technical side. On the data side itself, I think there is a identified need for infrastructure to be able to work with medical data. And this is one of the challenges that a lot of people in the field are trying to solve, basically setting up infrastructure to be able to de-identify data properly, to be able to verify that there are no patient information being shared, and then being able to build environments in which compute can be compute and the data can be brought together in a secure way. So all of these factors go into making improvements along this front.
Yeah, thanks a lot. We have one more question. Like, is it possible that one day, computer vision or like machine learning models can replace doctors for some specific tasks? Because like nowadays, like there are some models like which are implemented at various startups are there, like various companies are there. So like they implement models and like the models predict whether the disease is there or not, and like after that, like suggest you should visit a doctor. Like, is it possible to replace a doctor someday? And like clinical trials also not possible because yeah gone.
Sure. I mean, it's a good question. I think the way I think about it is that the use what a model can or cannot do is tied very closely to its intended use. If a model is intended to be used um, in conjunction with a doctor, then it's designed in a very different way than if it's intended to be used autonomously. There are examples of autonomous algorithms that basically decide whether or not, for screening someone's image of their eye, whether or not they should see the ophthalmologist. You could imagine a lot of other scenarios in which you could free up doctors that are trained to do other tasks by having these algorithms be used to support um, nurses or physicians in training that are not traditionally making these diagnostic calls. So a lot of setups that one can think about where algorithms are useful in an assistive setting or an autonomous setting. And I think whether or not they can replace doctors is better formulated as where can the algorithm be most useful.
Okay, and like it seems we do not have any more questions, so like we can end this here. And so thanks Pranav, that was a wonderful talk, and like we learned a lot in the application of ML in bio. And thanks everyone for joining. Like this was the last talk of MLRW 2022. This year we had a lot of interesting speakers from wide range of topics, like from industry, from research, from competitions. And that was an interesting experience for us also, and like we hope like you learned a lot, and let's see you next year. Thanks a lot once again.